Pessoal, muito boa noite. Bem-vindo ao primeiro evento aí do SQL Server DF de 2017. Espero que seja o primeiro de muitos. Mais uma vez a gente está fazendo essa apresentação em nome do PES, que é uma associação que todos já devem conhecer, uma associação internacional para nós, profissionais de SQL Server. O PES, além de outras coisas, subsidia e apoia diversos eventos da comunidade técnica, levando conhecimento a todos nós. O SQL Server DF é um grupo aqui de Brasília, que a gente teve poucos, mas temos eventos presenciais recorrentes. E hoje, com a grande presença aí do Bob Ward, que está nos presenteando aí com a palestra que ele fez no PS Summit 2016. E é uma grande oportunidade para a gente continuar enriquecendo nosso conhecimento. O SQL Server DF tem um grupo no Google, o pessoal troca dúvidas e tudo mais. Quem quiser participar, só entrar lá no link ou mandar um e-mail para esse e-mail aí que a gente vai fazer a aprovação aqui para você participar do grupo e ficar sabendo dos encontros e tudo mais que tem. Inclusive, palestrantes são bem-vindos. Quem quiser fazer uma apresentação, só falar com o Luciano Moreira, que é o Chapter Leader do grupo, que a gente agenda. E a gente está também orgulhoso aí do MTAC, Multi-Platform Technical Audience Contributor. A gente está nascendo uma ONG para apoiar esses eventos, palestras, tudo que a gente faz, não só Microsoft, mas todos de várias plataformas. Estamos inclusive aceitando a admissão de novos associados. Se você tem contribuições, ajuda a comunidade, entra aí no www.mtac.org, submeta a sua inscrição, que o pessoal vai analisar para você se tornar um MTAC junto a gente. Ok? Lembrando, a palestra vai ser em inglês. Eu vou passar a palavra agora para o Bob Ward. E vamos lá, está sendo gravado, ele autorizou, a gente vai ver isso depois. Mais uma coisa, a gente teve o SQL Saturday 573 em Brasília, em 2016. E prontamente já agendamos, dia 19 de agosto de 2017, a gente vai ter o SQL Saturday 618. Mais próximo do evento, vamos espalhar, vamos lotar, vamos fazer um grande evento como foi esse ano. Bob, can you hear me?
Okay, perfect. Hey, Edvaldo, thank you so much for having me. So my name is Bob Ward. I work for Microsoft. I want to first apologize to everybody on the phone for speaking English in your event. I wish I knew Portuguese. I wish I knew other languages. I hope you'll be able to understand everything that I'm saying today. I not only speak English, but famously speak Texan, which is kind of a joke. I'm from Texas in the United States. And so you might hear me throw some English phrases that you don't understand, and sometimes I speak pretty fast. So please, at any point in time in our talk today, don't hesitate to stop and interrupt me and say, hey, Bob, can you repeat something? I certainly don't mind that at all. Pretty passionate about this topic, so sometimes that even makes me talk even faster. So today's topic that Edvaldo invited me to speak on is on SQL Server 2016. And specifically, it's a talk about trying to really kind of convince you by the end of this session that you should take a hard look at SQL Server 2016, because it's my contention that making a move to this version of SQL Server can potentially have your application run much faster without any changes, with very little or no changes. And that was kind of a theme that we've been trying to present here at Microsoft for a while. So you see on this first slide, let me go ahead and move over just to full presentation mode. And a couple logistics about this. I'll go through these slides. I'll stop and do a couple of demonstrations for you, and I'll try to find some natural pausing points to stop and let you ask questions, either in the IM window or verbally or over the phone. But a couple of particulars about the talk. So first of all, I'm a big believer in everybody having decks and demos and things like that after you watch this recording. So if you go to this website, aka.ms/bobwardms, that's a OneDrive folder where I put a lot of my presentations up there for you to have access to. This particular presentation is available up there on the site. I have made a small change, something new that I'm showing for the first time for you here today, and I'll copy these slides and demos by the end of the week. I'm repeating actually this talk in an online event called groupby.org that Brent Ozar is running, and so you're actually getting a first look at what that's going to look like. I'm doing that this Friday, so I'll put the deck and demos up by this Friday up on that site, but there's a version of this deck that has much of the information already up there, demos already up there for you to run after the fact. Also, you might be interested to see that if you look at this website here, AK.MS Bob SQL, that points to a blog series that myself and Robert Dorr are running. Effectively, you could just search for the word Bob SQL on your favorite search engine and find a lot of the blog posts that we talked about. And we do talk about this topic in several places, and in fact, it's actually kind of where this idea was born. I love hearing from people about this topic, so bobward@microsoft.com is my email alias, and then you can see my Twitter handle @BobWardMS, or look for the hashtag BobSQL. A lot of the posts I do on Twitter, I'll use that hashtag BobSQL. So let me go ahead and start into this topic. And again, it's my contention that, I hope you're going to walk away today with the feeling or the inclination to go research more about SQL Server 2016, because I really believe that we've made substantial changes within the SQL Server engine that can allow you to get better performance without a lot of changes to what you're doing with SQL Server. So, but you might find interesting about how we got here. I mean, why did we start this theme? It runs faster. I mean, where did it actually come from? And I'll tell you a quick story. My colleague Robert Dorr, who I'm sitting here in Texas doing this presentation today, he's actually sitting outside my office. He works right outside my office here. And Robert Dorr and I both worked in the support organization in Microsoft. And a couple of years ago, as we were starting down the process of building SQL Server 2016, Bob started exploring with the product team things they were doing to the product that seemed to be making a substantial difference in performance. And he actually came to my office one day and said, Hey, Bob, I really think that SQL 16 just runs faster. I've got demonstrations and examples to show you that it just runs faster. And so that kind of, as he said that to me, I said, hey, that's a branding. We can use that. We can use the fact that it just runs faster and actually demonstrate and show technically to people why we think that's the case. And if you look at this first slide here, how we got there was a couple things. Number one, the observation from Microsoft that the SQL Server engine that we know and love that we built back in SQL 7.0 back in the late 90s was kind of showing its age a little bit, and it was showing its age specifically on new hardware systems. People were coming together with faster I/O, with network systems, with dense core CPU, high CPU type scenarios, and we were finding that some of the code we had built was not surviving and not running well in those environments. And how we experienced that was through customer experience, both from support cases, from direct customer interactions with labs and benchmarks we would do. We would use tools like Xevent and Xperf, and we came across these kind of themes of things that we started making changes to and why we made these changes. The first one deals with scalability. It was all about scalability. And in fact, I have a new term for you to learn today called reverse scalability. And that is customers having the expectations or having the experience, that they may upgrade to a certain version of a software product and even upgrade their hardware to something even faster and actually not get scalable results based on maybe a higher load they put on the system, but actually get worse results than they had before. So that's reverse scalability, right? And so we were seeing that type of behavior. So it wasn't just the fact that we weren't scalable, we were worse. So we didn't make sure that we were at least as fast, but even faster and scalable to these new hardware architectures. And, how do we achieve those kind of things? Well, one of the themes you're going to hear today is the concept of partitioning. Partitioning is a common computer science concept to achieve scalability in many systems and software systems. And you're going to see in many different examples where we chose to make decisions of partitioning things in SQL Server to achieve those results. Parallelism. You're familiar with the concept of running parallel queries today in SQL Server. Well, there's other parts of the SQL Server engine that we could achieve by doing things in parallel, like background threads running in parallel, those kind of things. In some situations, we decided to think just more and larger. We said, let's just do more of something. Let's add more log writers to SQL Server and see if it performs better. Let's do things larger. Let's change the size of I/O that we do with these newer I/O systems and see if we achieve better performance. Another thing that we kind of discovered that was important is that we wanted to be able to dynamically respond to something. So instead of SQL Server having a scenario where we would pre-build something to be scalable, we would react to a problem that SQL Server detected, and then we'd scale on the fly. So you're going to see an example of that today where we do a dynamic response for scalability. And then the last point is just improved algorithms. We just found parts of our code, things like spin locks and other parts of the system that worked great back in the late 90s or early 2000s, but with newer hardware architectures and newer thoughts about software algorithms, we need to make changes to those. And so we have several examples where we did that as well. One thing that's really important for you to understand is that nothing we did was intentionally designed for Enterprise Edition. You may have seen the announcement we made with SQL Server 2016 Service Pack 1, where we've kind of lit up new features, things like in-memory OLTP and column store that were previously only available in Enterprise Edition. Well, today, things I'm going to show you that we decided to make things scalable, nothing we made as a change was specific to Enterprise Edition and to any edition. There may be a feature I talk about today that's only available in Enterprise Edition, and we might have made that more scalable, but there's nothing specifically we did to say, hey, let's only make this faster just for folks running Enterprise Edition. So I think that's a very positive thing we did to ensure what we do applies across multiple editions. So before I get into some of these features that we did that allow you to make things faster in SQL 16, I want to make sure you're aware of two things. Well, two things that I've noticed from talking to customers about how to increase performance with SQL Server. There are features that we have had in the product that have been available since 2012 and 14 that do require some changes from you, but you can get incredible performance from them. For example, column store indexes. I would say, in fact, that's probably the #1 thing I would recommend anybody here on the phone in this meeting, in this presentation, that's listening maybe after the fact to investigate. If you've not invested in column store indexes and you run a lot of analytical queries, you should take a hard look at this. One of the top PMs that works in this space, I asked them, what are the typical query performance boosts you get from running column store? And he said 100x. And I said, hey, you're just kind of making that up. He said, no, I've got proof. I actually have worked with customer after customer after customer across the world and seen, on average, that kind of type increased query performance by moving to column store indexes. In-memory OLTP, which effectively known as codename Hackathon, involves a different type of technology, more oriented towards OLTP applications, but the PMs in that area said, hey, we can get 30x increased throughput for OLTP heavy intensive applications by moving to this technology. There's a little bit more required to move to that technology, but I want to make sure you're aware of these two if you're thinking about what investments do I need to make moving forward with what I'm doing in SQL Server. And again, these features are available before SQL 16, and we've made enhancements to these in SQL 16. You'll see an example of that today. Well, this is the list. This is a long list. This is a big list. And in fact, one thing I like to do in my presentations, you'll see several slides here where you'll have a hyperlink that you can click on after the fact. That will take you to somewhere on the internet to a reference point I want you to look at. And this, if you click on, will take you to all the blog posts. This list represents all the blog posts that have been done by Robert Dorr on this topic. When you see a little sticker that says the word new, this represents an area where we might not have done a blog post yet, but it's something we're going to do. The reason it has new is because I've done this presentation at large conferences like SQL Pass and Ignite last year, and these represent new topics that I've added to the agenda since some of these big presentations. There's no way today we could cover every single one of these. So here's what's interesting for you. If it's something that we're not going to talk about today, there are slides at the back of this deck called bonus material slides where I have created a slide on a topic that perhaps maybe I'm not talking about today. One of the examples is multiple log writers on this list at the top. Multiple log writers. It's something that's interesting that we've added, and I've got a slide that talks about the details behind it, but we're actually not going to cover that today's presentation. And when I say there are more, there are actually other blog posts we've done that I couldn't fit in the slide. In fact, this slide has become something that's interesting. I can't put any more on here. I have to go to 2 slides, I think, to actually create all the different topics we're doing. So instead, I've just created a summary slide of many important topics, and there are things at the back of the deck that talk about some things that are not even covered here. So let's move on, and let's go through a couple examples of core engine scalability in this topic, in this category. And you're going to see today in this deck, I'm going to cover a couple of different features or enhancements we've made in each of these categories. And then we'll certainly pause as we have time to go through questions. And in a couple areas, I'll stop and do some demos. I won't do demos for everything, but I'll do some in particular. So out of the gate, something called automatic soft NUMA is a very important core engine scalability that we've added to SQL Server. And to understand kind of how important that is, you have to kind of think back about the history of SMP machines and NUMA machine architectures. So, if you think way back into even the 90s, I remember in the late 90s, it being part of Microsoft, where I was given access to a Unisys server that had 8 CPUs on it, 8 physical CPUs. This is before NUMA technology, and I thought I was the greatest, incredible engineer in the world. I had access to this amazing server with 8 CPUs. That was called an SMP machine. And as SMP architecture grew from things like 8 CPUs to 32 or more, there were bottlenecks that were encountered within the hardware itself, because there's kind of this scalability point of 8, it seems to occur when it comes to CPUs. This bottleneck would occur specifically within the architecture of the actual hardware, like on the hardware bus, the memory bus. And so along comes this architecture called NUMA to partition CPUs into kind of like mini computers and give each NUMA node local memory access. So things were faster to access memory because of this NUMA architecture. And fortunately, the designers in our product team of SQL Server 2005, specifically guys like Slava Oaks, had the foresight to build NUMA into the product. Like SQL was aware of what NUMA looked like and could take advantage of that technology. But most of the original NUMA designs had no more than 8 CPUs per node, so you had a pretty kind of a nice system. You could have, for example, an 8-node NUMA machine back then, 8 CPUs per node, so you'd have 64 CPUs total, and things worked pretty well. But this concept of multi-core, came into play around the same time. And in fact, if you think about back in those days, you started with kind of dual-core and hyper-threading type processors, and now you've got this multi-core concept where CPUs in the market today have up to 24 plus cores per CPU. So as that comes along, now all of a sudden these NUMA nodes that have all of a sudden 24 more CPUs per node start experiencing the same bottleneck as the original SMP machines within the node, because there are more than 8 CPUs within a given NUMA node. And in fact, something like a spin lock that we use in SQL Server doesn't scale well in these large number of CPU scenarios within these nodes. So what are we going to do about this? We're not going to change the hardware architecture specifically, at least SQL Server's not, but we made some design decisions within the SQL 16 timeframe to do things a little differently, and we use this partitioning concept I mentioned earlier. There's the answer, partition it. So what we do now is, if we detect greater than 8 physical processors per NUMA node, we will split up and partition these hardware NUMA nodes within the confines of SQL Server, as we see it, into something called soft nodes. And it's on by default in SQL Server 2016. You have the ability with Alt or Server to actually turn that off or turn it back on. And so why do we do this? Well, any code in our engine that benefits from NUMA partitioning will now get a boost, because there'll be more NUMA nodes from a perspective of SQL Server than we had before. If you had a certain number of nodes with greater than 8 processors, we'll actually go partition these into a soft NUMA configuration, closest to 8 as we can. And so now naturally, because of partitioning, we'll get a boost. In fact, here's an example on the slide. We have something called an I/O completion worker within SQL Server, and the default behavior is, let's create one of these per node that we detect for connectivity purposes. This is the worker that's going to take the actual TDS requests, the logins and the batches from clients, and process these. So the more we have, the better throughput theoretically we can get. So this is an example where, without making any changes to I/O completion workers, we get more in the system because we have more nodes, so we can actually get better throughput. And one of the things you're going to see in these slides today is some actual examples of throughput. So look at the bottom comment there. So, we've taken workloads derived from some of our TPC benchmarks, and just by putting it on a machine, same hardware, and just by turning on AutoSoft NUMA, we can get a 25% increase in workload performance, because of the fact that there are many parts of the SQL Server engine that partition things based on NUMA nodes, and here we are doing it from a soft perspective. Let me show you an example of what this looks like, kind of in a more visual way, and then I'll stop and take some questions. So this is an example of a machine that I access frequently at Microsoft within our labs. And if you look on here, this is a 4-socket machine, and there's 1 node per socket, 18 cores per each CPU, so it's a multi-core machine, and it's hyper-threaded. So really, it's 36 logical CPUs with 4 nodes, so 144 total. So if you look visually at one of these nodes or one of these sockets, you'll see 36 logical CPUs. And think of these CPUs being numbered in the fashion that I'm describing here from left to right. And if you'll notice, I numbered these in an interesting way. I numbered these in kind of this vertical pattern here to show you that logical processors 0 and 1 belong to a single core. And if you'll notice, and you look across here, there are 18 of these across the way if you go from left to right. It's important to notice that, and I'll explain what I mean in a second. So when SQL Server looks at this situation at startup time, we detect we have more than 8 physical CPUs per node. In this particular case, there are 18. And so we say, okay, let's go ahead and break this up. And how are we actually going to go do this, right? So what we do is we take this given memory node 0 at the hardware level, and we break it up into 4 logical nodes. So you have the same number of CPUs, but SQL Server is going to look at these in a way that's mapped and you can see in this particular case, 9 CPUs per node. We took 36 and we divided it up into 9. Well, why did we pick 9? Because we're going to try to get close as we can to this 8 number that I mentioned earlier. It's kind of a magic number, right, of partitioning. But if you'll notice here, what's interesting in the numbering scheme is that we didn't put 0 and 1 on the same node next to each other, nor did we put 1 over here on the second node. And so what we try to do is we try to avoid putting 2 logical CPUs from the same core on the same node, because we're trying to avoid any CPU contention that could occur within the core itself. Second, if you'll notice, so we're skipping from 0, 2, and so forth, but you notice when we got to 16, we didn't put 1, 3, 5, etc. here on node 1. That's because when we do things like parallel queries, degree of parallelism, we typically schedule these things consecutively, sequentially across these nodes. So we try to avoid as much as we can putting subqueries from parallel queries on the same core. And so this is why you see CPUs 1 through 17 show up here in node 2 and not necessarily in node 1. So we try to get smart about how we're partitioning here. And the important point to note here is the fact that the hardware NUMA architecture hasn't changed. The memory node 0, from a hardware perspective, is still the case. We haven't changed the hardware. SQL Server has logically split up. Think of these as like virtual nodes. We've split up from a perspective of what these CPUs look like, and when SQL schedules work, it will use this soft NUMA concept to do scheduling for its worker threads. And I've got a very, very nice detailed blog post that I've added to our Bob SQL blog that showed you some examples of what this looks like. Especially, I've had some questions from people about what this looks like in a virtual machine scenario. So I've got examples to show you kind of what that looks like. Let me stop for a second, and I'll bring up the IM window and see if anybody's got any questions so far of what you've seen there. Any questions of what I've presented so far that you have about the overall concept of it runs faster, or specifically around soft NUMA?
Any question? Anyone? I have a question, Bob. Does it change the way you have the recommended way to configure the max degree of parallelism?
So the question is, Edvaldo's asking is, does it change our recommendations on max degree of parallelism? And the answer is no. If you look at one of the official KB articles that the CSS team produced, it takes an account for nodes, for NUMA nodes. And so given the fact that we're still using, if you look at DMOS nodes, which is a DMV that you can look at for a NUMA configuration for SQL, DMS nodes takes an account and shows this new logical breakdown of soft nodes, where DMOS memory nodes is the actual hardware nodes. And I believe our article recommends things based on DMS nodes. So no, if you take a look at some of our recommendations based on DMS nodes, it is now broken up and shows you these new soft nodes. So if you use that logic, you'll still be fine. For example, we'd probably recommend max DOP to be 9 here, right? Because each node only has 9 logical processors. Does that answer your question?
Yeah, great, thank you. That's okay? So let's go ahead.
Okay, so let me go back here and let's see. You can still see my desktop, correct?
Yes, I can.
Perfect. Okay. So again, after the fact, take a look at this blog post on the Bob SQL blog. A lot more details about what the DMVs would look like, how to break down what your error log shows you for nodes, things of that nature. It should give you more confidence. One of the key things before I leave this topic you should know is we build this in by default. So if you've got a machine that looks like with the specs like this, you don't do anything. It just works, and you get the benefits from it. Okay, well, another example in core engine scalability is something called dynamic memory objects, and this is a great example of this dynamic response capabilities that I mentioned early on the talk. So when you take a look at SQL Server memory, most of the memory you're used to seeing is in terms of like things like procedure cache and the buffer pool. And things like the buffer pool are usually built in terms of like 8K pages, right, database pages. That takes a large chunk of the memory SQL Server uses. Now, SQL Server, for the purposes of running its engine, has other memory needs to track things. We have other data structures that we use inside SQL Server to do various types of operations like connectivity. There's all sorts of things like that. Well, a lot of that memory is not specifically naturally into this 8K page scenario, right? We don't create 8K pages to store connection memory, for example. So what you have is, and what we do is we use this concept called memory objects within SQL Server to serve the needs of all these types of variable memory sized allocations. And this is similar to the concept in Windows of a heap. If you were a programmer writing Windows software, you might use something called a heap to do variable size memory allocation. So the problem is that anytime you build a system where you've got to track what are all the different memory allocations that are going on within your memory management system you've built, you have certain types of lists and data structures to maintain that. In other words, if you have inside SQL Server the need to allocate, 4 different 100-byte allocations, you must track the fact that you allocated these 100 bytes each. And if somebody deallocates that, you must maintain a list of these and remove something from a list. You've got to maintain and track this information. So what happens is when these memory objects are global, when many different threads in SQL Server can access these memory objects, you need to employ something called thread safety. You've got to find a way to ensure that one thread does not look at the invalid contents of another as memory is getting allocated and deallocating. And when you see contention occur because of that, you can see something called a cmemthread wait. If you've ever seen that inside SQL Server, and you've seen it at a very high level, in other words, a high number of waits with long wait times, that is usually a contention with something called memory objects. Now, we built SQL Server from the scratch when we built memory objects to have an infrastructure to partition these memory object structures by node or CPU. But we did not build by default a lot of these memory objects to be done that way because it can be a little bit of expensive. It can require overhead to do that. So some were built that way. Now, if a certain memory object was built with NUMA partitioning within its capabilities, you had this trace flag, 8048, that could promote and make a given memory object that was NUMA partitioned to be scaled to be CPU partitioned. So here's what happened over time. Customers would contact support and say, hey, I've got a cmemthread wait problem. We would discover some sort of memory object. Maybe it's related to spatial memory, connection memory, some sort of memory need. And it's not something you control. It's something within SQL Server, the design. And every time we would find a hot one, we'd have to create a hotfix. And the hotfix would entail us taking that memory object and partitioning it by node or CPU. Well, we would run into these like 2 or 3 times a year. And over time, this got to be old. A customer would call us, we'd create a hotfix. We'd fix one, we'd fix another. And so, we said to ourselves, there's got to be a better way of doing this. And in SQL 16, we did. We created a new system. We created a dynamic response system that can actually try to look at and see whether a cmemthread wait scenario is occurring. And as it's occurring, we can dynamically partition a memory object to a node or CPU scenario. First, we partition it by node, and then if we still have contention, we partition it by CPU. And it's quite interesting. This is a small little chart here that shows you the behavior that you can run into. And this red line represents these waits that are occurring, and then this green line represents batches. And as SQL Server right here in this inflection point responds dynamically to the problem, the waits go to almost nothing and the batch response goes up. So this is us dynamically scaling on the fly based on us responding to a problem that SQL detects. And in fact, my take here is that this just works. You don't even know this is going on. This happens so quickly in these scenarios that it's something that SQL reacts to very, very quickly and solves for you. And we've seen a 3x improvement in memory allocation with less CPU overhead when we can actually trigger this behavior. Let me stop for a second and show you kind of a demonstration. This is kind of a fun little demo to look at of what happens. I've got a perfmon chart here where I'm tracking processor time, something called thread safe memory object waits, which is equivalent to your C memthread wait type, and batch requests per second. Now over here in my Management Studio window, I've got a couple of queries, and all this stuff is available to you in the demos. If you look here, this one is a very complicated query, but what it's showing you is new information we've added to our DMVs to show us, are we seeing contention going on with this memory object? And over here to the right, if things get partitioned dynamically, this behavior will actually change. So if I run this particular query here, I can see that this memory object, or something we call PMO, is not created to be partitioned, but is partitionable. It's possible we can do that depending on the problem. Now, it's interesting. We've actually built in a trace flag, a undocumented trace flag, to turn off this feature just so we can demo the problem. If I ran this this demo without doing that, the problem would fix itself so fast you wouldn't see the behavior. So in this command line here, I've got a little stress test where I could actually run and go see this behavior. So I'm going to run this, and I'm going to go over here and I'm going to go look at this chart. And it's going to show me, am I having a contention problem? And you can see here the purple line is the waits. So you can see the waits are getting up to like 48,000 created per second, and the batch requests are running somewhere around 3,000. And so what I'll do is I'll go ahead and just turn on this feature, again, by using a trace flag, and go back and observe perfmon. And if you look here across the top, you will see here something that's very interesting. You will see here in the purple line that the waits make this climb down here, down to almost nothing. In fact, let me pause this to show you. You'll see the waits were up here pretty high, and the batch requests per second were running here at around 3,000. And here's our inflection point. The waits go down and the batch requests go up. In fact, the batch requests are going to go up to somewhere around, if I can hover over this correctly, around 3,800. So I was down here around 3,000, I went to 3,800, and then waits went to nothing. Now if I keep running this and play it, you'll observe something else that's interesting. So here the waits are going down, the batches are going up. Notice also that processor time has gone down. So processor time was up here around the 50-60 range. Now processor time here is around the 20 to 30 range. So this is a great example of the waits going away, the number of batches that we can process going up, and processor time going down. Now you may think of in terms of waits that are occurring in SQL Server and wonder, how is it possible that you can get high processor time and then it go down because you're having waits? That's because in this scenario, the waits that are occurring have spin locks as part of their behavior. And so when you see a highly contentious problem in SQL Server that involves spin locks, all of a sudden now what you can see have happen here is you can see processor time kick up because spin locks are kicking in. Now if I go back over here and I look at this DMV, you'll notice here are some changes. It's still not created a partition, but you'll notice this has changed, that we automatically, dynamically partition this by CPU. So again, I use the trace flag only to pause the behavior so that you can see the problem. And then when I turned off the trace flag, which is turning on the feature, you can see we partition this within seconds. Within seconds, we changed our behavior that the waits would go away. We'd get a more smooth execution of batches per second and less processor time. I think I saw a question come up here. Oh, okay, that was just a comment. So again, this is a good example of SQL Server scaling on the fly, dynamically responding to a problem, and this is core built into SQL Server. And this is one of the interesting things that I show customers where, hopefully you won't even know this has happened. You will never see it before. You get an appreciation of something we've put in the engine that gives you core engine scalability. Here's another core engine scalability feature you'll find very interesting. I also have a demo for this as well called Parallel Redo. So if you're not familiar with how SQL Server does recovery, I've got a nice little link to a primer here Paul Randall's written on how recovery works. But effectively, when we run recovery on a database, we have three phases. The analysis phase is where we scan the transaction log based on a certain point of the last checkpoint up to the oldest end of the log. The oldest active transaction down to the end of the log is what we do. So we analyze what has to be done. We have to do the redo phase. The redo phase, of course, is where we actually go take a look at transaction log entries that are committed in the transaction log but the pages on disk are not reflective of those committed transactions, and so we have to read the page from disk and read those operations, and then finally we have to undo. In other words, we have to go in to find transactions in the transaction log that were not committed, that did not actually got rolled back, and we have to go find pages on disk that are reflective of those transactions, and we have to undo those changes. So that's kind of the phases of recovery, and so we're talking a little more about the redo phase. And you may ask yourself, what's this parallel concept and why are we going redo? Well, typically what's happened in the past, the redo phase is a single-threaded operations for each database. And it's been I/O bound. If you think of what I just described to you, you read a page from disk, you go through and you apply all the changes to that page based on committed transactions. And so really the time it takes to run redo is typically how fast can we get these pages from disk and make changes to them. And so what we found is that faster I/O devices came into play where the latency to read these pages was minimal. In fact, it wasn't very, very, very slow at all. It was very fast. And so we realized that our redo code was bottlenecked because of the fact that we were single-threaded. And we needed to push the CPU harder to make redo faster. And so think about the scenario with a secondary replica for always-on availability groups. That's a continuous redo scenario, right? If you have a secondary replica, we're always applying logbox and then running redo all the time. And so the redo portion that we have to do, we have to make sure those logs are hardened and we're running redo. We don't want to slow the primary down, right? So running redo is really important for us. So the redo, since it's about playing these changes to pages, we needed to go through a process of doing these things in parallel. And so we read the page from disk and apply the log changes based on LSN. But here's the problem we thought about, is that we have to make sure we do things in the right order or we'll get inconsistent. So here's the algorithm we came up with. First of all, we decided to take normal worker threads from SQL Server, because we're only doing this during recovery. We'll take normal threads from SQL Server and we'll build a worker pool of these. We'll dedicate some worker threads to doing parallel redo during the process of doing a recovery of our database. And we could be doing this for multiple databases at the same time. So the reason I have the word parallel redo task is that's the actual name of the command you'll see from dmexec requests when we're doing parallel redo. And what we decided to do was we have this concept called a dirty page table. A dirty page table is something that's built during the analysis phase of reading the log. What we're doing is we're going through and we're making a record of which pages actually that are on disk that need to be changed for redo purposes. What are the pages that need to be dirtied and made a change based on log records that are committed that have not been committed on the page. And so what we did is we just partitioned this table to apply things in parallel. So effectively, each task is going to be assigned a given page to work on. And then we have a chain or a list of the log sequence numbers or the log records that must be applied in order for that page. By doing this, we've done a couple of things. We've partitioned out the work. There's that partitioning word again. So we can do things in parallel. We can do it faster. And since we only allow a given task to work on a given page and all its log changes, we avoided any consistency problems. In other words, this task here assigned to page 2 can't skip over and work on page 1 because we need to make sure that we apply these changes in LSN order correctly to achieve consistency. So a great example where we've partitioned the work, but we've done this in a way that we achieve consistency, so speed plus consistency is done and achieved. And in fact, we can easily demonstrate that an 80% increase can be seen from using standalone recovery redo single-threaded type algorithm. So let me stop for a second and show you an example of this, and also show you some new feature that we've added that's actually really nice about recovery. So first of all, I've got on my SQL Server a X event session that uses some new extended events that trace how recovery runs in SQL Server. So if you're trying to actually take a look at a slow-running recovery, you can actually use this technology. So let me just double-check that this X event is running. In fact, here it is, recovery traces, that's listed right there. I'm going to go ahead and start that session. Now, something interesting that I built with this X event session, if you look over here, I have this option, startup state equals on. Now, if you think about how recovery is going to work here, I'm going to force SQL Server to run recovery by restarting SQL. And since this X event session is only on when SQL is running, if you add this startup state equals on, SQL Server will start this X-event session before recovery is run. So X-event is running, and you can trace the behavior even before SQL has fully made this database available. I have this script that I've already run right here, where I've truncated the table and I've inserted data into a table and deleted table from a table. Now, if you look here, and I've already performed this operation, and if you look here and think about how we want to reproduce this behavior, you have to think very carefully about how to reproduce a redo scenario. Remember, what redo is a scenario where SQL Server has committed transactions in the transaction log, but the pages on disk are not reflective of those committed transactions. So first in order, what we must do is we must run some actual changes to the database and make sure they're committed. That's the first thing we got to do. But one of the problems here when you make a lot of changes is that checkpoint could kick in, either an indirect checkpoint or a normal checkpoint. So up at the top of this screen here, you can see where I took and changed the indirect target recovery time and made it really long. So what this means is SQL Server will run all these changes, but it won't checkpoint the database. So now I've created my conditions of this problem. But I can't shut down SQL Server cleanly or else a checkpoint's going to get run. So what I can do is I can go over here with Task Manager and I can find SQL Server as a process. Now, obviously, you're not going to do this in production. Please don't do this in production. And I can end the task. And that's basically going to kill SQL Server in a fashion that will not allow it to do a clean shutdown. Now I can come back over here and I can restart SQL Server as a process. And what's going to kick in is it's going to run recovery against that database. And then what I can do is I can go over here to my X-event session that we talked about, the recovery trace session, and I can bring up this X-event session and see what it looks like. Let me see what happened there and make sure. Yeah, these are the two files right here that I'm looking for, but they did not. I probably did not start this session correctly is probably what happened. Let me go back here. Oops. Let me go back here and stop this trace and delete these files real quickly. Okay. And let me go back and let's run this again. Let's see, let's delete this session. And let's go back and recreate this session again. Okay, now we've got that. And let me go back and rerun these queries again right here. Let's see, let me go down here. Okay. And let me run these again. So what I'm doing, by the way, is I'm just truncating this table, doing a bunch of inserts into this table, then doing a bunch of deletes. So basically, I'm doing a lot of operations in this table to do a lot of committed transactions. And then I'll go ahead and kill SQL Server again, and then we'll go look at, let me just double check that my session has got back here. So it's here, but it's empty because I'm not running recovery yet. And let me also, while we're doing this, let me go look at the error log file. Oops. Let's go double check and see what this looks like. Yeah, I wanted to make sure that transactions got rolled forward here. So you see your 6 transactions rolled forward. So let's go back and see if this is still running. Any questions about this concept of parallel redo while I'm still waiting for this to finish? I think it's still running here. So there's a question here about, is it possible into a latch contention? And your question is it a latch contention between the parallel thread? Between the parallel threads itself, there's no possibility of running the latch contention because of the fact that each of them have their own separate page. What we have seen in some cases is issues on secondary replicas where parallel redo is running, and a customer is running really high intensive read workloads, what we've seen is some contention that occurs there, but it's not at the page latch level. We're still kind of investigating whether that's really a huge bottleneck for customers, but I have seen some contention occur on a secondary scenario. Let me go ahead and end this task and restart SQL Server. And I want to show you the recovery algorithm here. Let's go. Okay, it already finished. Let's go here. Let's refresh our X event session. And okay, there we go. Now we see some information on here. And I'll come back to your latch question in a second. So if you scroll down here, you're going to see all sorts of information that's going on about a way to trace what's going on in recovery of your database. So this isn't just to show you the fact that parallel redo is running. It's also a tip for you that if you have long recovery problems, you could potentially use this type of X event session to go determine where is recovery in this process. So if I scroll down here to the bottom, I will see information about my database. This was called Insert is Faster 2016. That was my database. And notice here, you can see message like this: redo worker is starting up on schedule. And notice the 2 is indicative of more than one redo worker in parallel running. And if I scroll back up here, I can see things like parallel redo pool size of 4, parallel redo enabled for database. So you can see information about the fact that we are running things in parallel, and look at the different worker threads and what they're doing. So that's how to look at see a redo. In the slide deck in the notes section, there's a comment there about an undocumented trace flag where you can disable parallel redo only for the purposes of seeing the different behaviors. So if you ran this demo and turned that trace flag on, you would see it would take like twice as long to actually go run recovery for this database. If we go in the error log here and look at it, you can see that recovery, in fact, one thing that's interesting about our error log, you can see the total time it takes to do recovery. In this case, it's only 2 seconds. But if you turn this trace flag on, you'll notice here that we don't run it in parallel, and it'll take twice as long to do things in serial. So the question here is that what determines the number of redo threads? It's also based on cost threshold. It's a great question, Edvaldo. The redo thread decision is not based on anything to do with max degree of parallelism at all. It has to do with us deciding how many worker threads are currently in the system, and we have determined that a max of 4 redo worker threads is the most we'll build for a pool for a given database. So it's not based on any kind of threshold algorithms at all, and it's only based on to make sure that the current workload. In other words, I believe there's a threshold that if we have too many databases running each 4 at max, that we'll throttle that down, but it's simply more of a fixed size based on our testing that we've done. It says here this feature change, if any, works the way TempDB works. And as far Fabiano, are you asking that question in terms of parallel redo? Yeah. So no, this doesn't. As you may be aware, we don't do recovery for TempDB. TempDB is not a database that's recovered; it's recreated every single time you restart SQL Server. So yeah, parallel redo would have no effect on anything that we would do for TempDB. Other questions? Okay, let me go ahead and move on here. Let's kind of switch gears a little bit and talk about DBCC. I'm sure you guys have used DBCC and you care a little bit about its performance. I'm sorry, is there a new question coming up?
Sorry, no, I'm not getting to move this line.
Hello? Okay, so I think maybe somebody had unmuted themselves accidentally.
Yeah.
Okay, so let's talk about CheckDB a little bit. So in SQL 2008 timeframe and a little bit around 2008, 2012, we made a conscious effort to try to make CheckDB faster, specifically focusing on the with physical only option. That's the one we thought we could get the best bang for our buck from trying to make performance changes. And you can see here some links that we have here. We would try to improve things like latch contention problems on something called a multi-object scanner latch and batch capabilities. Several things that we made changes to, right? And the reason I have this comment, get me disk speed back up to null test, is the following. When I think about CheckDB and what's required to run CheckDB with physical only, that's the one we're focusing on. The speed at which we can run CheckDB is really dictated on how fast we can read the pages from disk of the database and then run an audit check on those pages. So yes, there's CPU that's required to run an audit check on those pages, but it's really more about how fast can we read these pages from disk. And the reason I compare this to backup is that that's what backup does. If you do a backup of a database, we read the pages from disk, and then we're going to write the pages to the backup medium. If you use this trick, backup to null, and the word null is not misspelled, it's N-U-L in quotes, that's just an old trick that you can use. If you do a backup to a disk equals null device and run it, that is effectively going to test how fast can SQL Server read pages from disk and then write it to nothing. It doesn't get written to anything. So my thinking is when we're looking at CheckDB physical only, I want to compare what is the read rate, what are the I/O rates of backup to null versus CheckDB physical only. That's our goal. That's what we really want to get to as much as possible. And so in 2008, we made changes that get us close to that. But we knew we could do better. And in fact, in 2016, we take things to a new level. We discovered actually this multi-object scanner latch, which is not a page latch, but a special latch we use for concurrency with parallel CheckDB. We discovered that it had severe scalability problems. And in fact, if you really get high number of CPUs in SQL Server where CheckDB is running in parallel, that you got this reverse scalability concept. And we thought this latch was holding us back. And so we took this no-lock approach. In fact, some of the developers that worked on the in-memory OTP project that were used to doing things without latches looked at the code and said, hey, I don't even think we need this latch anymore. I think we can do things that protect the parallelism of CheckDB threads, but do it in a way that's still safe and gives us better performance. And so 2016 includes a change that behind the scenes you can't even see where we don't even use this latch. And so our read-ahead capabilities of reading ahead and getting pages from a disk to perform CheckDB is greatly improved. And in fact, here's the results. I call this a typical SAP database, which is based on a database with a large number of objects at a 1 terabyte size. We out of the gate with no changes to an application, just running CheckDB with physical only, we would get 7x performance faster. And the more degree of parallelism, the better performance. Now there's still a point where there's a threshold where you don't get a better performance after a certain number. But we were getting great results. In fact, I could take small databases of only 5 gig in size and get 2x faster performance just by the changes we made internally to CheckDB with physical only. And this is a chart that I show that one of the developers gave me. It's an interesting chart here because the higher the bar, the worse is the problem, because this is actually the time it takes to run something. So degree of parallelism is on the x-axis, and you can see here that as you add more processors, you get worse performance. That's that reverse scalability problem. But as you see here in the changes we made from the orange bars, we get faster or as good performance as we add processors to the mix. And so again, 7x faster performance for a 1 terabyte database for running CheckDB. I've got another slide at the back of the deck that talks about some other changes we made to CheckDB. You may ask yourself, does a full CheckDB, take advantage of these changes and this performance benefit? And the answer is yes, potentially. But you got to remember, a full CheckDB, one where you don't specify physical only, has so many other things to do, and how many indexes you have, and how deep they are, and how much checks we have to do on logical checks and so forth, can affect the speed of CheckDB. So really, what we're targeting here is how to make physical only as fast as possible. So let's talk a little bit about TempDB. TempDB, a passionate topic from a lot of people. And if you think about the history of TempDB, one of the most contentious and one of the most widely discussed topics about it is multiple data files. How many data files do I need for TempDB? And for the longest time, a lot of people, and even Microsoft documented, that you needed 1 file per processor, basically. And so we had people out there with 256 processor machines with 256 data files. And back in 2011, I did a talk at the SQL Path Summit. I've got a link to that right here, where I kind of proved and demonstrated that really 1 per processor, gets to a certain point where it doesn't make sense. And so my kind of rule of thumb was, create 1 data file per logical processor up to 8, and then go add by 4, add increments of 4 until it doesn't help anymore, until you don't see a performance gain. And the thing that's really important that I need to remind you about TempDB and files is that it's nothing to do with I/O. Sure, it is true that sometimes we do I/O for TempDB data files. Let's do a quick review here. For TempDB I/O, for the data files themselves, the only time we're going to write data to TempDB database files are A, you're low in memory, and so Lazy Writer must flush out user temp tables, right? Because we don't checkpoint user temp tables to TempDB data files because we don't need to because we don't do recovery. But we have things like sort spills and hash warnings and things that do sometimes require us to write out to TempDB database files. So we don't do I/O as much in TempDB. And so yes, you could take advantage of spreading your files across disks. If you're an I/O bound scenario with TempDB, that's possible. But really this multiple data file is more about spreading access to these important allocation pages, GAM, SGAM, and PFS. And really, if you think about it, when you use multiple data files, you in a way are partitioning the allocation of TempDB because it's really the speed at which we can allocate pages that matter in these typical TempDB scenarios, because you're often in this allocation, deallocation, a create and destroy situation. Think about the typical TempDB scenario with user temp tables. You create a temp table in a procedure, and the procedure finishes. Well, what are you doing? You're allocating pages for that TempDB object, and you're deallocating pages for that TempDB object. And you do this a lot. So, again, multiple files make sense. Well, in SQL 16, we've done two things. Number one, by default, out of the gate, we are going to create one TempDB file per logical processor up to 8. And we're going to, in setup, provide a new tab for you to take these defaults and make changes to them. So you're looking at my laptop here, which I have 8 CPUs, in which these are the defaults that were picked. 8 files, basically, one logical CPU up to 8. You can increase that during setup if you'd like. One PFS interval up to 64 meg, which is the size of a PFS interval. The autogrow is set to that. That makes it a little bit more efficient when you're actually having autogrow has to kick in. We also allow you to actually add these files to different directories. So if you did want to spread these files across drives or folders, you could add in these folders right here, and we would round robin put these files into these folders or directories. And then finally, the transaction log is now 8 megabyte by default as well. So those are the defaults, and then the setup tab here allows you to make changes to those defaults out of the gate. So, does it even matter? I mean, does it matter that we've changed this to 8? Does it matter that you have chance to do that? Well, I went back to this inside TempDB talk I did at PASS in 2011, and I grabbed the demo that I used back then, and I reran it on my laptop. And you can see over here to the right the results. I took a SQL Server 2014 instance of my laptop, and I did no configuration. It's just out of the box. I didn't change 14 at all. And then I took 2016, and I didn't change it at all. And I get 2x performance, at least, by doing that. 8 data files, 8 meg, no autogrow. And, of course, with 2014, I only have 1 data file by default, so autogrow got hit, plus I get this massive contention. And then look over here to the graph to the left. This is the graph that I used back in 2011. And you can see here with 1 file, it matters a lot. And if you go to 8 files, look at the substantial increase in performance you get. This is a duration test. So the number of seconds of duration for this repro, this demo, is on the left-hand side. And here is actually on the right-hand side number of files. And you can see here, as I went to 32 files, things actually kind of got better for me. But by the time I got to 64 here, there's really no difference. This is kind of showing you that difference about moving to 8 and then increasing by 4 until you stop seeing a performance. In addition, I have a slide in the back that talks about these trace flags. And these trace flags involve 2 ones. Trace flag 1118 deals with how we allocate extents for databases. And, we always recommend using trace flag 118. You can even see here the increase in performance I get by turning that trace flag on. Well, in 2016, that trace flag is on now by default. In fact, the trace flag doesn't even exist anymore. If you turn it on, you get a warning in the error log that the trace flag doesn't exist. It's been changed into an alter database option. Trace flag 1117, which we also recommend for TempDB, is now on by default. And that says when you do an autogrow of a file, you autogrow all those files at the same size. So if you have 8 files over here, and they're at 8 meg, but I need to kick on an auto grow. If one of them grows, I will auto grow all of them at the same time. And that's really, really critical because I cannot achieve this balance of round robin proportional fill on TempDB unless everything is the same size. I'll get this skew where everything lines up onto one file if I don't do that. So out of the gate, 2x faster out of the gate on an 8 CPU machine with no configuration. It is true in 2014 that if you changed TempDB and you configured it exactly like SQL 16 does out of the gate, you could achieve a similar performance. I'm simply comparing an out-of-the-box test. You install 14, you install 16, you made no changes to either one. I've got a contention that TempDB now just works for you and actually is faster for you without making any changes to the actual product itself. Let me just double check here and see if I've got any new questions that have popped up. So it says right here, CheckDB has the same performance in Enterprise and Standard. And Fabio, so that's Fabricio. Yeah, Fabricio, your question is yes. That change we made for CheckDB is orthogonal to the version. One thing I'd have to check, though, is whether parallelism for CheckDB is allowed in Standard Edition. I'd have to go double check whether that's the case or not. I'm not sure. Because the changes we made are only going to really help you if we can run CheckDB in parallel. The other question is, what actually is the multi-object scanner latch doing before, what was actually used for? It was used to protect data structures inside SQL Server as we were reading pages from disk, and we were going through multiple objects and having to figure out which page belonged to which object to check them. So we used a latch to protect these threads running in parallel to ensure this data structure where we were tracking these pages was in sync properly. So as a latch we needed to actually do the proper checking of CheckDB, but we determined that we could still do things in a thread-safe manner without the latch. What would the dot performance limit be on CheckDB? I think that's one you're asking. And I think that varies depending on the type of machine that you have. So you have to test that for yourself. There's no fixed number about what would be the degree of parallelism that would be a cost-benefit threshold for you where you no longer saw any benefit to performance. It's not something that's fixed. It would be based more on the system that you have. You'd have to do some testing to see what that threshold looks like. And another question over here is, multiple files can degrade the performance of sort operations in TempDB. And I've not seen that behavior before. That multiple files could degrade the performance of sort operations. If that's something that you have a scenario where you've actually seen that to be the case, I'd love to see that. When we do sort spills to disk in TempDB, we allocate pages, and we're going to use the same proportional fill algorithms that we do when we're creating user temp tables. So we should still be able to spread the load across these files and avoid any allocation contention. So I've not seen any degradation of performance of sort operations just because you have multiple files. So another question here is, sorry, which metric is it seconds for what? What was that question in regards to? Oh, in the graph for TempDB. Yeah, that was the duration of the workload. So I had a demo that you can get from the demo directories that I have up on the share, on this OneDrive share. And so basically I took an O-stress test tool that we have, and I ran it for a period of time. I ran it for a certain number of users for a certain number of iterations, and seconds was the total duration for the workload test itself. So the total workload time went significantly down as you increase the number of TempDB files. It says here, is it possible that TempDB is replaced by another memory structure in the future? No, and so to be really, really direct to you, William, about your question, there's no plans that we have to change the architecture of how TempDB works from a perspective of different structures. But one thing I will tell you, and there's no details yet behind this, but we always take a look at how we can improve TempDB, and so we are taking a look at other ways to make optimizations so that TempDB can be more efficient for you. I will tell you that in relation to your question a little bit, I've had several customers lately take in SQL 2016, take a hard look at changing from using temp tables to memory optimized tables, to in-memory OLTP memory optimized tables. So they've changed that workload to say, hey, I was using temp tables before, or even table types, which get stored in TempDB, or table value parameters with table types. And I've moved those to memory optimized tables and seen significant increases in performance. There is some changes required to do that, though, to your code, to your T-SQL code. but I have seen customers do that. Another question is it possible in the future to have TempDB for each user database? That is certainly something we're taking a hard look at. No commitments about what we're doing in the future, but we've had that request a lot, and it's certainly something we're taking a look at. Any other questions while I've got it paused here about TempDB? Okay, let me move on and talk about I/O. I/O is certainly a passionate topic for a lot of people. There's this feature and this topic called instant file initialization. This is a feature that's been around since SQL 2005 that we've allowed. And in fact, that name, instant file initialization, is our name. It's not something specific that you can find out there. And here's what it means. I think it's important you understand a little bit behind what this means and why you really care about it. So prior to introducing this feature in SQL 2005, the speed to create a database was the speed to write zeros to the disk file. So if you had a 10 gigabyte database file, the fastest we could create that database is the fastest we can write zeros to every aspect to that 10 gig file. So how fast can you write 10 gigs of zeros to a file, right? So, we knew that we needed to make something faster here. And so Windows came along with this new API called set file valid data. And the way this works is, as a programmer, as a developer, is that, and this is what the SQL engine developers did, you tell this API, here's a file name, and here is the length I want you to create this file. I want you to create 10 gig file. And basically this API would come back within the snap of your fingers and say, good, here's a 10 gig file. Okay? So creating a file for a database became almost as fast. It was just as fast regardless of the size we're creating. But how do we handle these zero concepts? I mean, how does that actually work? Well, so we would write zeros before to the disk for a database file, but when this feature came along, we realized that we didn't need to do that anymore. Within SQL Server, we format pages as we use them, or we format the transaction log as we use it, right? So we said, okay, we'll use this API call right here. And excuse me, transaction log is different, but for a database file, we didn't need to write zeros all the time to a disk. But we did need to make sure that zeros were seen for the file for certain situations. And here's what I mean. So for a create database statement, you may not care about the speed of creating a database file, right? I don't care if it takes 15 minutes to create my database on my laptop. I'm going to go get a cup of coffee or go to lunch and come back. But you do care about restore and auto grow. Those are scenarios where we need to grow the size of a file or create files. And those operations, you do care about the speed for those. So you like the fact that we're using this functionality to speed up the creation of a file for a database. Because it could be autogrow could be a major blocking problem, because autogrow occurs by us growing this file in the context of a transaction. So the way this really works here is that if this performance volume maintenance task privilege is set, and by the way, I can never remember the name of that. It's kind of a hidden thing for me, and it doesn't really make sense to me. That's the name of the privilege, and I'll explain why it's important in a second that we've made a change here in SQL Server. Windows admins have this by default. So what happens here is that when this privilege is set, and you call this API call, any bytes in the space of this file that you created that was on disk before can be seen by a person who has this privilege. But anyone else sees zeros. So if you were to go to the file system on your NTFS disk and look at a file created in this fashion, and you're a Windows admin, you could go look at this file and see the bytes that might have been for somebody else's Word doc or something in the past, right? But if you weren't an admin, Windows would present to you zero, so you couldn't actually see that. So it doesn't really matter for SQL Server because the SQL engine has certain privileges to do what it needs, and then admins, of course, have privileges in the box anyways. And for the transaction log, we rely on a known byte pattern. So we can't use this functionality. It's not the fact that the transaction log cannot use this functionality because of some limitation of Windows. It's the fact that we rely on a known byte pattern, so we need to make sure that we just don't see whatever bytes were previously on disk for this file. We see specifically a known set of byte patterns, so we can't use this functionality for transaction logs. But for database files, we can. So since you care about this for restore and autogrow, you do want to use this feature. But we did not turn this feature on up until SQL 2016 for you. So what you had to do is you had to go in and add in the SQL service account to this privilege by using a program called the local policy editor. Well, who can even remember when that should be done? So what we did in SQL 16 is we did two things. Number one, when you're going through setup, when you specify the service accounts, you have a new checkbox to check on and say, hey, the SQL Server Engine service account has this privilege. So no longer do you have to remember after the fact of installing SQL to do this. Second of all, we have a new installer for Developer Edition, Evaluation Edition, and Express Edition. And this functionality is turned on by default when you run those installers. If you've not taken a look at our new installer for Developer Edition, you can basically install now SQL Developer Edition in 3 screens, 3 clicks and you're done. And we would turn on this feature by default. And there can be a significant performance increase. I've got a demo where you can run and look at the fact that if you don't use this feature, it could be 200% slower to create a database of, say, 10 gig, even on your laptop. Whereas if you have this functionality turned on, it can be that much faster to do it. So the change in 16 is to offer you during setup the ability to do this. The new installer is turned up by default, and it's something that I see a lot of customers miss when they're setting up SQL Server. So now in 16, it's a lot more easier to do it, and it can have a significant impact to you when you're restoring a database or an autogrow has to kick into SQL Server. Okay, let's talk another topic about I/O called persistent log buffers, and I love talking about this one because this is kind of an advanced topic. So if you think about the evolution of storage, and you look at some of these nomenclatures here, you think about typical hard drives. You might think in terms of a typical SAN drive, and the latency in these drives being somewhere around like 7 to 8 to 10 milliseconds. And then you move into the original SSD technologies, and the latency in these drives, the transfer rate of these drives could be somewhere like 1 or 2 milliseconds. Well, look at this symbol right here. This is microseconds. And there's a new type of drive that's been available now for a little bit, and it's called a PCI NVMe SSD drive. And if you've never seen one of these, I have one on my laptop right here I'm doing this presentation on, and it almost looks like a little memory stick, but it's actually really a hard drive, an actual hard drive that is in your system. So the latencies and transfer rates for these are like in microseconds. Well, if you're tired of write log waits, if you think about sometimes what the bottleneck is for an application, let's say in-memory OLTP, you still have to write out data to the transaction log. And a write log wait is typically the amount of time it takes us to write out to the transaction log for any kind of log commit operation. So along comes a new technology called NVDIM, or persistent memory. And this little nomenclature is nanoseconds. So in Windows Server 2016, they support a new concept to take advantage of this new technology called NVDIM, which is now a thing produced by certain hardware manufacturers. This type of actual drive, it does also look a little bit like memory, but built into the machine. And Windows 16 provides 2 interfaces to this type of storage. One is called block storage, which is your standard file system storage, and you're going to get a benefit. In fact, it's going to be faster than this type of PCI drive, SSD drive, just by using this. But what's really interesting is this new interface called Direct Access, or DAX. And what you're going to find is you're going to start seeing speeds. If you can use this direct access functionality, you're going to start seeing speeds closer to this even nanosecond type speed. So here's how it kind of works. You would format your NTFS volume with this new DAX parameter on Windows Server 2016 should you have one of these special drives you could buy from a manufacturer. Today I've seen the early ones that come out are very small in size. They're like 8 gig in size. I think you're going to see them get larger and larger. And you may ask yourself, well, what am I going to do with an 8 gig drive when my transaction log has got to be bigger than that? Well, here's what you do. You format this new NTFS volume that recognizes this drive with a special parameter DAX. In SQL Server 2016 SP1, when you create your database, you actually create a second transaction log file on this new drive. So you create one log file that's on your normal drive. Maybe it's on an SSD drive. Maybe it's like 100 gig or something. You create this new transaction log that's small in size on this new DAX volume. Now, what SQL Server does is it recognizes this automatically. And the current active log that's in memory, what we call the tail of the log, we can now do a memory copy of that tail of the log to this new DAX drive, which again can sometimes be in the speed of nanoseconds. We copy this over, and then we can let the commit proceed at that point. And the reason is because when we copy this log, this tail of the log, into this NVDIM, it's now persisted. So even if the machine crashed, the transaction log data is still considered to be good and persisted on disk. what happens is once we've determined that we've copied this data to this new NVDIM storage, we can lazily behind the scenes take that tail log and write it to your full transaction log, which is now in your normal drive. But that's all in the background. So now you get something really crazy. You get write log waits that will show up as 0 milliseconds. In fact, I think it's very interesting if you think about this. The DMVs, like DM exec requests, the most granularity they have is in terms of milliseconds. So you might see a write log wait that still shows up as a valid wait, but the wait type is 0. That doesn't mean you're not waiting. That means that the wait is less than a millisecond. It's probably something in terms of microseconds. And I've got some great videos for you to go back and look at to see kind of what the behavior is of this technology. And it's a great example of us not just keeping up with technology, hardware technology, but staying ahead of the game. So the combination of Windows Server 2016 plus SQL Server 2016 SP1, you can run and you can actually get into some amazing our product team about how this technology works behind the scenes and some of the numbers and performance numbers they've seen from this. So, PCI NVMe SSD drives can potentially give you microsecond performance, and now you can get even faster performance from that by using this whole concept called NVM DIM. Let me stop and see again if we have some more questions here. If I don't enable IFI in the installation, 16 has an easy way to enable it later. It's the same process other versions. So, the answer to your question here is that 16 has no changes to enable this later. The thing that we've done specifically is allow you to add this during setup. So, yes, you still have to go through and set up the performance volume maintenance privilege using the local policy editor if you didn't during setup. But to remind you, if you're using something just like Developer Edition, we'll put that on there for default for you. Okay, let me switch topics to something kind of completely different on something we did with Windows Server, SQL Server 2016, and that is something called Windows Functions Go Batch. And I've got the nice little Microsoft Windows icon, but that's a little tongue-in-cheek. This has nothing to do with Windows operating system per se, but something called Windows Functions. And so we had this concept called batch mode processing that we added back before SQL 16 for column store indexes. And the concept being is the fact that we can now process certain rows of data while we're running a query for you in batches versus row by row. And that speeds up things tremendously during certain column store query operations. Well, also before SQL 16, back in 2012, we introduced this concept called Windows Functions. Window functions. Windows functions have nothing to do with Windows operating system, but more specific query syntax using this keyword called over, where you're allowed to process data and do operations against data within a query that's separate from the rest of the query. And a lot of amazing type of functionality can be achieved by using these window functions in T-SQL, where if you really struggled before with doing group by operations and subqueries and multiple self-joins, and you really struggle with all of that because you're trying to do something really special with a set of rows, I highly encourage you to take a look at these things called window functions. And I've got a really nice primer for you from Itzhak Ben-Gan, who's a famous MVP, who goes into an exhaustive detail of what these are. This is an example of the syntax. So you could have this operation here with a sum and using this over clause, and inside here is what's called the window. And this row's unbounded preceding and current row from is a frame. And then you have a function called a sum. You have all sorts of different functions at your disposal you can apply against this. The way to think of this is being able to process a set of rows kind of independent from the rest of the query, but yet getting the results from it. So for example, sometimes people use this to run past the limitation of doing group bys, where you have to include certain columns in the select projection clause that the group by requires. So it's pretty neat technology. I really, if you've never experienced window functions or don't know what they are, and you find yourself frustrated with sometimes running a lot of subquery type operations, take a hard look at that. In this particular case, you can see we're running a sum over this partition, this window partition. And this rows unbounded preceding key syntax is really interesting because it allows you to actually process data within the rows themselves. So this unbounded preceding from current row allows you to do things like running totals. Like if you want to do running averages or running totals within queries, you can do things using this type of syntax. And so the key thing is that we've allowed this technology before, but in 16, we took a look at Windows functions and said, hey, let's apply some of this batch mode capabilities that Column Store provided, and let's allow you to do that against these Windows functions. And to the right over here shows you a graph where this batch versus row mode has got incredible performance gains. So you can see here that this using this row mode internally within SQL Server, the degree of parallelism as it goes over time kind of flattens out on your performance, but look at the scaling we can achieve by using batch mode. And the way we achieve this is we have a new operator we've introduced called the Windows Aggregate Operator. Let me just show you briefly what that looks like. So I'll go over here, and let me kind of get rid of this here, and this window here. And I've got some examples. These examples look fairly complex. So I won't go into depths of the detail. I'll let you kind of look at them. Just to let you know, though, that I've got two tables. One is a table called clickstream, which has got a column store index on it. And one's called clickstream row, which is a heap, which doesn't have a column store index. So this particular demo is really trying to simulate and show someone what are the number of clicks by an IP address to like a website. Like if you were trying to track how many times somebody had clicked something and how long was the duration of when they clicked it within a certain time frame, these are using some of these window function examples. The lag function allows you to check and look at the difference between a previous row and a row before it. And then we're using the sum with the same concept of doing this row unbounded and current row. So I've got, in fact, if you look at this query here, this is using common tabled expressions. I've got a with clause, another with clause, and then a select using the two table expressions above it. So it's a fairly complex query, but it shows you the power of this. So this is the exact query using the clickstream row table here, which is not using column star indexes. So let me kick this off and run this. This over here, this demo is using the clickstream table, which is using the column store index. So I'm going to kick that off as well, and both these are now running. And so it's the same exact data, except one's got a column store index and one doesn't. That's the only difference. And so SQL Server is able to detect that this column store index exists and use this aggregate function. You see, this comes back in 14 seconds while this is still running, even though I ran this beforehand. And if I go here and take a look at the execution plan, the query plan, you're going to see a new operator show up. And that is something called the window aggregate operator. And you can see here the execution mode is called batch. And this actually shows up twice because of the fact that I'm using two of these window functions. Whereas if you go over here, this is the row mode query. This took 29 seconds, same data, same exact set of data. One is a column store index and one doesn't. And you can see with these window functions here that one is twice as fast. And if I ran this on a machine that had more processors, I could scale and get this even faster. And if you go look at the plan for this, you can see a larger number of operators that are being applied here with hash joins and something called a stream aggregate. So quick example here of how we took a set of queries that people like to do with new technologies called window functions, and just by applying a column store index, SQL Server can apply a new batch mode technology against it, run things in terms of batches instead of row by rows, and achieve really, really fast performance. And the really fun part about this demo, to be really candid with you though, is the fact that if I go look at this particular server right here and run add version, you can see here that I'm actually doing this against a Linux server. So this is also to show you how serious we are about Linux. This is actually a VM running on my laptop, running the new SQL Server Linux public preview on Ubuntu. So, and to be honest with you, it didn't take very long for me to set this up. It took me no more than about 15 minutes to get the Ubuntu downloaded, get SQL Server installed, and to simply run. And this actual same demonstration, the setup script, the queries, I was able to install this both on SQL Server on Windows and Linux with no changes at all. There's no difference between how I installed both the actual demo itself. I created a database, installed my data, and now I'm running things twice as fast on a Linux server demo as I am on Windows. Let's see if there's any questions here. Let's go back here to persistent log buffer. Is there any way to take advantage on persistent log buffer without a PCI storage? So the NVDIMM technology, I don't believe it requires PCI, but I've not looked physically at those hardware devices. NVDIMM is different than PCI NVMe SSDs. You specifically need to have a device called NVDIMM, though. You can take a look in the Windows documentation of what that looks like, and the manufacturers that produce those type of hardware. In SQL 16, Windows functions are fully implemented as ANSI determines, for instance, limitations on frame until range. That's a great question, and I'm not knowledgeable enough about Windows functions to know the answer to that question, but I'd love to research for that for you. So if you could just send me an email at bobward@microsoft.com with your specific question, I'll get you the answer to that. Okay, let's kind of finish off our conversation here. I realize that we probably have about 3 minutes left, so we've answered a lot of questions in between. I think that'll help us, right, in seeing what questions you have at the end. Let's talk about always-on availability groups. So, always-on availability groups, I think, is an amazing technology we introduced in SQL 2012. I think the design we built is very, very good. But one thing that happened to us as SQL 2014 came to light and customers started using that version is we found that customers were starting to really put in some high-powered hardware, not just on the primary, but also on the secondary. So what would happen is a customer would contact us and say, look, I'm putting up a brand new system. I want to use always-on availability groups, and I want to use a sync replica. But performance is being impacted on my primary when I set up the sync replica. And what we found is that our code was not scaling. Our code was not keeping up with the faster hardware we had built. So early customers that had put this stuff on, in fact, for years customers had put this on, and the standard hardware they had built for the primary and the secondary, our code was fine because the bottleneck was occurring more at the hardware level. It was either the I/O on the secondary maybe, or it was the network system, or maybe they didn't have a secondary built with a large number of CPUs. So as customers built up these more high-powered boxes to even run their secondary sync replicas, they found that they were having performance problems. And so they were like, hey, where's the performance problem if I make this as fast as possible from a hardware perspective? And we took a hard look at our code. In addition, NMLTP is a technology that relies on the log. We still have to have transaction logs that are used for MLTP transactions. And so since it's in memory, the bottleneck is typically the transaction log. And if you put this in a availability group scenario, we need to make sure that it's definitely doesn't need to be slowed down by scenario where we can't harden our log records on a sync replica scenario. And if you didn't know this, behind the scenes, Azure SQL Database for high availability uses always-on availability groups for replication, for geo-replication. So that team said, look, you got to make sure that this thing is running very efficiently for us, and your code is not the bottleneck. But we found out in some cases that the code was the bottleneck. So we came up with these goals. We said, first of all, in SQL 16, we want to make sure that if you have a single sync replica, our benchmarks that we set up could run 95% as fast as if you didn't even have a replica. So if you set up a SQL Server with no AG installed, and then you put AG on and had a single sync replica, we want to be 95% as fast as that standalone speed, right? And then second, the header sync commit wait type is something you can see when you've got a bottleneck on a sync replica scenario. So we said, hey, on small to medium workloads, we want to be less than 1 millisecond on average with these latencies. And so here's all the stuff we did. We took an overall look at the architecture, and again, the overall design was good. This was a tuning of the architecture to meet the needs of new hardware systems. So here's an example. We took a look at the number of threads and context switches that were required to initiate a transaction on a primary, harden the log on the primary. At the same time, we're shipping these log blocks to a secondary and harden the log on the secondary. So we realized it took 15 worker thread context switches just to do that round trip. And we took a look at the design and said, improve the communication path. We have the ability for the log writer to directly submit the log blocks to the secondary if the secondary can keep up with the log writer process. We did things in parallel. We added multiple log writers. We did parallel log redo, which I've already shown you today. We implemented that on secondaries. And we took a look at areas where we were doing spin locks and we limited some of those, and other areas of the code where we thought we were being inefficient. So it was kind of a way for us to kind of wake up and say, hey, we need to keep pace or stay ahead of new hardware systems and ensure our code is scalable in those scenarios. And I'm proud to show you the results. Take a look at this graph. And let's kind of go through this on the right-hand side. On the left-hand side is to show you a little bit of the specs we use with the machine. And there's a blog post I have here that we've already posted here, I did last year, called Always on Turbocharged. So if you look at this graph, pay attention to the blue line. The blue line represents the speed of this benchmark that we did, this OLTP best benchmark, for a standard standalone, for a standalone workload, not a standard, but a standalone workload. Okay, that's the performance we got. So on the bottom here is the number of concurrent users, and on the y-axis is the throughput of the log on the primary. So as the number of users increased, we want to see that throughput continue to go up and scale, and eventually it does hit a tipping point here with a certain number of users. But here's the key. The yellow line represents that same workload if we set up a single sync replica for always on with SQL 2014. So as you can see here, the performance is greatly different between the blue and the yellow line. That's not good. That means we're not keeping up and we're not meeting the goal of 95%. The orange line represents SQL Server 2016 with a single sync replica, and the gray line represents a single sync replica with encryption turned on. So you can see, based on this benchmark test we did, we were able to achieve 95% of standalone speed with a single sync replica, 90% with two replicas, 90% with encryption, 85% with two replicas with encryption. And our latency goals were met as well. And here are the processor specs in general of what we used. It wasn't like, this is a pretty nice machine that we used, but it wasn't like we used the most powerful server we had to put on the planet to make this happen. And so the point here is that you too can achieve this performance with always on, provided you have the right hardware specifications on both the primary and the secondary. So here's some of the things that we've blogged about in the theme of SQL Server 2016. It runs faster. You can go read about those. There's various types of topics. And here's some stuff that we haven't blogged about yet. So we still would like to continue to add to this story in other parts of the product that we haven't really actually talked about yet. And you can continue to look and see that we're going to make new blog posts about this topic. Here are some references for you. To take a look. If you use this particular URL, you'll get all the different blog posts. The SQL Cat team has some blog posts they've done that kind of overlap with some of the topics we've done as well. And then here's a pointer to what's new in the database engine for 16 that you can take a look at as well. And then, as I mentioned before to you, in the back of this deck, there is bonus material for all sorts of topics that I have. There's a laundry list of all these other topics that I didn't cover today that you can read in more detail if you look at the back of the deck here. So we're just about 3 minutes over the time that we said that we would spend today, an hour and a half. I hope you found this to be valuable and useful. Are there any other last questions that you might have about anything I talked about today?
Anyone?
Well, hey, if you run into something that you saw today or you see later that you'd like to know about, Bob Ward at Microsoft.com. I'd love to hear from you. And anything at all on this topic you think would be helpful. Anything at all in the SQL 2016 space that you think, hey, I heard you said it was faster, but it's not running faster for me. I'd like you to look at it. Or more details about what you see in this deck, I'm happy to answer at another time. But I really appreciate your time today. I hope you found it helpful.
Bob, thank you very much for your time and for your presentation. It was awesome, amazing, very useful, and we learned very much. I really, and I'm sure everyone here appreciated that. Thank you, and thank you everybody who attended. And as Bob allowed us, we're going to make this video available and for watching it later. Thank you very much.
Thank you, everyone. Have a great evening.
Have a good night. Bye-bye.